All right, guys. So I'm not the best drawer, but this is my plane. The printer at work, it just still not working, but it's all good. So this problem is telling you, hey, what are the reactions at the gears, right? You have a nose landing gear and you have two main landing gears. Now, I work in the aerospace industry, so I thought this problem was pretty cool. You know, back then when I was in statics, I used to do these problems and I mean, I didn't care about any of that, right? You guys don't either. You guys just want the solution, and I get it. But you know, it's cool looking back at these problems and trying to like understand why you're doing them to begin with, and that's kind of what I want you guys to start like opening up your minds to, like why are you doing this to begin with. So in this case, they're asking us what are the reactions at the gears, right? So just FYI, and before I get started on the video, I just want to explain. Just hear me out, right? I work in this industry, okay, and I work as a structural engineer at one of the one of the major contractors for defense, and we support production, right? They're building the plane, right? Take the B-2 for example. The B-2 is a bomber, right? They build it. They were building it back in the 90s, but they built it, and you know, as they're building it, things mess up, right? You know, it's a whole process. You know, they mess up fittings, or they gouged it. You know, they created a scratch on it. So all that becomes MRB. And when you get a chance after this video, Google what an MRB engineer is. Okay, those are very common roles anywhere in the industry, and if you could do that, you will have a job for life. Those roles are always in demand. Sure, certain programs come down, right? But there will always be a program that's being in production. And we're knowing how to be a structural engineer in that. There's also liaison engineers. Other people call them MRB engineers. There's a lot of people that support production. And in this case, this problem is kind of cool because I've had it in the past where production manufacturing will come to us and engineering, right? And they'll specifically stress engineering, and they'll be like, hey, look, we're trying to jack the airplane 20 feet higher, but you know, this is what the situation is. We have this much fuel on because we were testing fuel, but it turns out we have to jack it up per this requirement and all this other stuff. And that's where you got to come in and be like, all right, can we do it, kind of thing. So this is one of those problems. It gets a little more complicated, but you guys are just level 2, level 1 college students, right? Freshman, sophomore, you guys are taking statics, but that's kind of what this problem is asking. Okay, so just FYI. So in this case, they're saying that the weight at point A, which is the center of the fuselage, right? That's what they determined it. It's 45,000 pounds. At the wings, in a traditional aircraft, and mostly every aircraft, the fuel is stored in the wings. Okay, so at point C, you have 6,000 pounds coming straight down. It's fuel, right? It's just weight. And at point B, you have 8,000 pounds of fuel. And I mean, they're just asking you to find the reactions, and there's more to it, right? You don't just find a reaction, that's it, you call it a day, right? What do you do with those reactions is something else, and don't worry, you'll learn that in future classes. So in this case, you got 8,000 pounds coming down at B, 6,000 at C, 45,000 at A. So what are your reactions at this gear, and this gear? Okay, so step one, I did a free body diagram, and I put the coordinates just in case I needed them. Now, the cool thing is I'll steer off for like another couple seconds, but you could solve this problem using FEA, okay? Now, you guys will not take FEA. You guys probably won't, right? Unless you choose it. It's an elective. It was an elective at my school. Maybe it's not at yours. You got to look into that. But I was a mechanical engineer, and I chose to do FEA in my 4th year. And you can actually solve this problem using these coordinate systems. And this is a space thrust problem. And I already actually have videos on my channel, but you guys will not understand matrices just yet unless you're taking linear algebra. But even then, try if you're curious, you could probably follow it and you'll be all right. But I mean, don't worry about it. But I put these coordinates just in case I needed it. Notice how they didn't give us z's. And look, these coordinates, A, B, and C, they're at a specific height, but they didn't give you z. And it doesn't matter, right? It doesn't matter where, because at the end of the day, you just have forces and reactions going in the z direction, right? Up and down. There's nothing left to right, side to side, blah, blah, blah. Nothing in the x, nothing in the y, just pure z. So none of those are going to cause a moment about z, right? Anything going along that axis is never going to cause a moment about that axis. So you don't even need a distance for z, if that makes sense. And you'll see it as you go along in the problem, but that's kind of like what you should kind of see intuitively. So let's just kind of keep going, right? I'm gonna go to the next step, step 2. So for these problems, I always like to do some of the forces in the x, y, and z, wherever I can, okay? X, Y, and Z. In this case, if you do some of the forces in the x, nothing's going in the x direction, right? X direction is this one right here. So in this direction, nothing's happening. So it's just 0. Some of the forces in the x is equal to 0, so that means f of x is equal to 0. In the y direction, it's this axis right here. Well, nothing's going in that direction, so that's also 0. So just like that, remember, in all these problems, you want the 6 things. Forces in the x, y, z, moments in the x, y, z, okay? 6 equations, 6 unknowns is usually what the situation will be most likely on your exam, just FYI. But in this case, it's going to be very simple. So just like that, x and y are 0, right? Fx, Fy is 0. Now Fz, okay, cool. So you have the reaction at F, the nose landing gear, the main landing gear, and the main landing gear. It's 2 main landing gears, okay? And the reason they call it main landing gear is because when the plane lands, it lands on those 2 main gears first, and then the nose hits. So these should always be better reinforced, okay, than this one, just FYI. And you'll learn that once you're in industry and you start looking into the drawings, how they designed it. But this is the equation you get when you get to some of the forces in the Z. Sorry, it's a lot of wind, if you can hear it. But some of the forces in the Z, okay? It's reaction at F, which is a nose landing gear, main landing gear, is equal to 59,000. It's just the sum of all the other ones. B, A, and C all come down. 45 plus 8 plus 6 will give you 59. Okay, cool. So now that we did all our forces, now we're going to go to the moments, right? So what could we do? In this case, I did some of the moment about Z. And I know you're probably wondering what the hell how will I know where to take a moment about, right? And that's kind of where you got to put your mind to it, right? Like looking at the problem, what can you do? So pretend I didn't even know I was going to take a moment about Z. Like, what would you do, right? In this case, look, I could take a moment about Y. C is going to make a moment about Y. It's going to make counterclockwise. A is going to make a counterclockwise moment about Y. B is going to make it about Y, counterclockwise. F is going to make it clockwise, right? E and D are on the y-axis, so they're not going to do anything. So I could have done Y, and I'm pretty sure I do, right? But I just started doing it about Z in this case. F is not going to do anything about Z. A is not going to do anything about Z. So it's kind of what I told you guys earlier, right? If it's going in the direction of Z, in this case, you're going to have nothing, no moment about Z. And don't get confused, right? You see A coming down, you might think, oh, it's this A times the distance to Z. That's not how that works, okay? Because you're never going to spin about Z. Does that make sense? Only X and Y direction forces will make moments about Z. Only Z and Y forces will make a moment about X. Only, assuming they have a distance, right? Because force times distance equals moment. But that's kind of a general, like a generic rule of thumb, right? Okay. If the force is acting in that direction, it's never going to create a moment about that axis, okay? And that's what's happening here. They're all going in the Z, so you're never going to have a moment about Z. So let's go to step 4. Okay, I went this way. I'm trying to understand. Yeah, step 6. Okay. So now I did some of the moments about X, and that is 0, right? Everything's equal to 0, it's statics. And you guys will never have to worry about that. This is a statically determinate problem. You will never have to worry about indeterminacy right now. That's later in strength of materials. But right now, it's just statically determinate, meaning you should be able to find all your reactions using the summation of forces and moments. That's it. You don't need deformation compatibility. That's what they call it. And you'll see that in later classes. But in this case, take a moment about X now. Right? Okay, so what's F's not doing a moment about X? It would have, right? Because it's going in the Z direction and it's not in the X direction. So it could have made a moment, but it's going through it, right? There's no distance. Force times distance. That's what you need. So in this case, this doesn't do anything. D is pushing up and it's going to create a clockwise moment about X. Okay, you're going to go this way. So it's going to be a negative D times distance. 8 plus 6, 14. So negative D times 14. Okay, and then B is going to create a positive. It's going counterclockwise about X. B times 6, right? That's the distance. 6 comes down and then this way. So B times 6, and that's here, plus B times 6. A doesn't do anything because it's coming straight through it. It would have, but again, it goes through the axis, just like this one. C is 8 meters. Is it meters or feet? I think it's feet. I didn't write it down. It doesn't matter. It's C times 8. And that is coming this way, and that is clockwise. So that's a negative C times 8. Then E is going this way, and that is counterclockwise, right? Because it's going this way, about X. So it's E times 6 plus 8, 14. Cool. Now, just like that, we got it. We know A, B, and C, right? Remember from the top? So that means we know these two. So just like that, we could get it in terms of D and E. And just like that, after doing the math, you'll find that D is just equal to E. Okay? And you're probably looking, before I continue, you're probably looking at this like, well, how's that possible, right? You have 8,000 pounds coming down here and you have 6,000. So wouldn't one be like, wouldn't this gear be taking more load than this one? That would be true, assuming the distance from this to this was the same, from B to D and then from C to E. But it's not. Look, B to D, you're 8 meters away. C to E, you're 6 meters away. So C is 6,000, okay? And actually, I set it to the gear, but you actually have to do it to the axis because that's kind of where you're taking the moment about from. So in this case, B is 6 meters away. So B is 8 times 6, that's 48. C is 6,000 times 8, right? Because that's your distance to the axis. So that means it's 48. And yeah, it's kind of equal and opposite. So they will equal each other. It does make sense is what I'm trying to say. You might look at this and think it doesn't, but it actually does because of the spacing. Okay. So just like that, we found a relationship between D and E. We don't know what they are yet, but cool, at least we know it. Now, what we do next is some of the moments about Y, and that's kind of what I said earlier, okay? If you do some of the moments about Y, let me cover that. If you do some of the moments about Y, F, okay, the blue pencil is Y, okay? F is gonna make a clockwise motion about Y, right? Okay? So that's going to be a negative F times your distance. 20 plus 3 plus 4, 27. So negative F times 27. That's what you see here, okay? I'm sorry. Let's go back to the diagram. D and E won't do anything, okay? Because they're on the axis itself. B is going to do something. B is coming down, so it's doing counterclockwise. And it's at a distance of 4. Okay, so plus B times 4. A is coming down and it's at a distance of 7 to the y-axis, and it's counterclockwise about y, so it's a positive A times 7. C, same thing, counterclockwise about y, so it's positive C times your distance 4 plus C4. And just like that, you find that F, once you plug in all the numbers, right? B, A, C, you know them because they're just your weights. I put W, A, W, B, W, C, same thing. But you plug them in and you're able to solve for F. And just like that, you have found your F. Boom, okay? Now we're going to use this relationship by plugging in F. Now we just know E and D, but guess what? They're equal to each other. So you could just do what I did here. From step 2, F is equal to F plus E is equal to 59,000, right? I just replaced that D with an E. That's all I did. And then I already know F. So now 2E is equal to that, right? Subtracted F to this side, and I got this number. And just like that, the reaction gears, the reactions at the main landing gears are equal, just 22, 630. And there you go. That's kind of cool, right? And like I said, if you're curious, that's where the video ends. So that's the answer. But like going back onto like working in aerospace production, right? The reason you do this, right? Once you get your reactions, you know how much load this gear is bringing into your wing structure, okay? And there's several load cases. Usually when you work, if you ever work in this industry, you'll see that when they design this plane, there's a lot of load cases, okay, like gust, maneuver. So it's like, pretend like your arm, okay? Look at the arm. So this arm right now, there's nothing being applied to it, right? But guess what? What if I twist my arm? Well, now I'm creating torsion, and you don't know what that is yet. Don't worry about it. But now I'm creating torsion. Before I continue, there's 4 internal stresses that are always produced, okay? Shear, bending, torsion, and axial. Shear and torsion produce shear stresses. Vertical shear, okay? Vertical shear and torsion produce shear. Bending and axial produce normal stresses. And you'll need that later when you start doing strength of materials. But look at my arm again. If I do this, it's all torsion. There's no shear, there's no vertical shear, there's no bending, and there's no axial, okay? Now, what if I twist it and I also pull it? Well, now axial, right? I'm pulling it, so, and then I'm also twisting it, so that's torsion. So that's 2 internal shears. What if I now twist it, pull it, and also push it down? Well, now I'm developing 3 internal, right? Torsion, torsion because I'm twisting, axial because I'm pulling, and then bending because I'm pushing it down here. So right along up until my shoulder, you can't see it on the camera, but on my shoulder, it's bending. It's creating like imagine like a diving board. You're jumping in a pool. You're jumping at the edge of the diving board. Well, guess what? If that thing were to ever break, it's gonna fail at the other opposite end of that diving board. It's creating bending along that beam, and the mode of failure is at the very end. Okay. So, and then as you press down on it, you're also creating vertical shear. So that one actually has 4 internal loadings. The reason I bring this up is because when they design a plane, there's several, those using those 4 internal loadings, stresses, they design it to that, if that makes sense. Like the plane can experience a combination of loadings, and they have to design that, hey, the worst case, this is what's going to happen on the airplane, and you have to design the structure to ensure that happens. So the reason, going back to the production thing, if they want to, let's say, move the plane from one building to another because they have to for whatever reason, well, now they're going to get a stress engineer. Hey, it has this much fuel and we're looking to move it. Can we do it? And you know, you come in as a stress engineer, find reactions, then maybe like, okay, my keel, right, the structure of the beam inside the wing, it's this thick, this wide, these dimensions. Like, will the stresses being produced as they move it from building to building, will they like withstand, right? And that's kind of what you do. I'll just keep it simple in that sense. It's very interesting, but that is what I do for work. So I thought this problem was pretty cool. But yeah, that's the answer. That's the top, and then that is the bottom. So I hope that helped.